Good evening. Uh, welcome. Welcome you for sixth session for our doubt session uh, for the basics of finite element analysis part one course under the NPTEL. So, meanwhile, while others join, can I know your feedback? How is the course going so far? It's 6 weeks has passed by now. So, Mr. Anja, are you there? So, may I know your feedback for the course so far? Hello. Yeah. Am I audible? Yeah. Hello. Good evening. So can you guys confirm if I'm audible? Okay, thanks. So yeah, it's already 6 weeks have passed for this course. I would like to hear your feedbacks if anyone wants to share how is the course going for them so far, and then maybe we'll start. So and we haven't done any introduction for the participant of this course so far. Is it possible for anyone to unmute themselves and just give a quick introduction why they are taking this course? So yeah, anyone would like to introduce themselves and give some feedback for the sport so far? So already 6 weeks have passed. Anyone like would like to volunteer? Yeah, hello. So Mr. Paolo, how is your experience so far for this course? Yeah, it's really basic. Yeah. Mhm. Yes. Even I have been following this course. So after a long time visiting FEM, there are a lot of basics. Yeah, yeah, exactly. So it's basically focused on FEM. Although the course is under the mechanical faculty, so some problems are so there's some kind of bias for solid problem and thermal problem. But yes, it's quite basic. So I have also been following this course. I have it's been a long time since I have had touch with the FEM. So yeah, there are a couple of basic things that even I had forgotten or not gone through. It's a learning experience for me as well for basics. But yeah, for solving more realistic FEM problems, there's a long way to go from here. Okay, thanks for the interaction. So yeah, welcome for this the sixth sex doubt session for the this basic FEA course. And until the last week, we had just started off with the introduction to heat conduction problems, heat conduction with convection. So of course, this course is basically focused on 1D. So we just consider the 1D heat equation with convection. So we know the governing equation for the 1D heat equation with convection, and then we can get the weak form as we have been doing so far. We get the stiffness matrix term, we get the force vector terms, and we get the boundary terms as well. Yeah. So uh, ignoring the convective term, we to remove the convective term, what we need to do is just remove this beta term, and then simple conduction problem. And the assembly is just as usual. We have what we have been doing so far. So whatever the common node is for two elements, we follow the continuity condition for the primary variable and add the force terms at the common node. And for extra unknowns, we use the boundary conditions, and that's the way we solve any basic FEM problem. So we just visited basic 1D heat conduction problem, and then we started with the Euler-Bernoulli beam theory. So as you might have studied in solid mechanics, the basic some basic assumptions for Euler-Bernoulli beam theory. The very fundamental one of them is the plane section remains plane and normal after bending. So this kind of assumption is more suitable for long beams and having less thickness, suitably considerably less thickness, and also the deformed angles are small. So the for Euler-Bernoulli beam theory, we get the governing equation for deformation like this. So basically, this is nothing but the uh, this okay. So this is the equation, and we'll be following certain sign conditions for these problems. So as usual, the upward direction is taken as positive for deflection and shear force, and for moment and slope being clockwise is taken as positive. So this is the general sign convention we'll be following. So now this type of equation is a fourth order equation. So that's the unusual thing about this type of problem. That's why we are studying it separately. It's so the heat conduction and that axial deformation bar problem was totally identical. The same equation, same type of boundary condition, everything was same. So, but in beam problems, the equation is now a fourth order equation. So we have considerable differences here. So now the integration by parts is done two times, and we get two separate terms for this uh, but this boundary term, and so the our degree of freedom per node increases. So since we have two primary variables now, we one is the W, that is deflection, and one is another one is the slope. The It is a derivative of W. And then for secondary variables, there was something we studied in earlier classes to identify the primary variable and the secondary variable using the boundary term. So if we substitute in the boundary term, we have the weight function and the coefficient of the weight function. So this is the weight function. So if we substitute the primary variable with the weight function, whatever we get is the primary not the primary variable, but yeah, uh, by primary variable means the one we are solving here in the equation. This term. If we substitute it here, whatever we get is the primary variable, and whatever the coefficient is left, that would be the corresponding secondary variable. So it's like here also, if we substitute the W here, we'll get W dash, which is again minus of W dash, which is against the another primary variable, and the corresponding coefficient is the secondary variable. So
Hello.
Yeah.
I have a doubt actually.
Yes. Yeah. Tell me. Please go ahead.
So, after completing this 8 week course, the where exactly do we stand in terms of understanding FAM completely?
Can you repeat? I missed you in the in between.
After completing this 8 week course,
Yeah.
where, where do we stand exactly in terms of
Oh.
understanding FAM completely? Like, can
So
you tell it on a scale of 10? Like, how much is that
10.
how much more to learn?
That would be a rather difficult thing to do, or scale as on putting it in a scale. But as far as my understanding of this course is, this is mainly 1D course. So you would know all the fundamentals, that's for sure. You know where FEM comes from, what are the approaches, and pretty much you're done with the basic after this course. 1D, in 1D we, it's not like one in 2D or 3D we do something unique. There is the common basic way to approach the problem that you for sure you'll understand, but you might have to get experience with the 2D and 3D problems. So there are a couple of things to be done later, which are very trivial in case of 1D, but not so trivial in 2D and 3D. I might have told in earlier classes about connectivity metrics. So I even showed a connectivity metrics for 2D elements. That's something not very trivial in case of 1D, but not very trivial in 2D. So I think you would need, on the scale of 10, I would say that you will be there by around 5, 6 maybe. You would need to. By the way, I think there's another part of this course, right? This is FEA1, basics of FEA1. There's part second also. So maybe that might cover the cover it the part which is left after this. I'm not sure. I haven't seen that course, but even after doing 2D and 3D, you might have to learn how to solve these problems numerically using software or even computer code. For personally, I learned FU with by two courses. I had to take two courses. One was the basic fundamental course, and another one was applied course. So I think 5 or 6 is my judgment. Uh, I hope there's no other question. Should I move ahead?
Yeah, yeah, okay. Thanks. Thank you.
Yeah, no problem. So yeah, so now in the beam problem we have two primary variables and two secondary variables. So the interpolation is going to be more complicated and a little different. So we get the weak form, we get the bilinear term, linear term, everything. So the next thing is to find out the interpolation functions. And so okay, so there are two things. So first, on first node we have the deflection W, and we also have the slope theta. One. And on another one we have deflection and slope. So our interpolation should be such that we should get the required values for the W. So our W element should be such that at the respective node we should get the required value of W, whatever it is, and plus we should get the slope of W, required slope of W, like this. So basically what we do is we take a common variable, take this one is U1, U2, U3, U4, and when we'll put these conditions, so at first node we should get this is U1, and on the first node this should be the deflection, this should be slope, this at second this should be deflection, this should be slope. So we'll get couple of conditions. There's a lot of equation involved here, and that we can just go through it, and we'll see that for each fee we have four conditions. First, the two conditions are on the value of fee, and two are on this derivative of fee. And so, if we have four conditions, we can get a third degree polynomial uh, for its. So we have, since we have four equations, we can get the value of four variables. One, two. So we can get a 3-degree polynomial. And solving all this, we get all these complicated polynomials, and we can even plot them and see if that we'll get the required value of slope and the value at the corresponding node. Okay, and so doing the finite element formulation for Euler-Bernoulli beam, we have the Stiffness matrix term and the force vector term. Now it's pretty much the same, but we need to watch out for the continuity condition. So so we have the process of solving this and getting this is rather difficult. Maybe I'll try to show you in the class at the end how we got all this, but it's rather it will take time. So the main thing is the assembly part of this. So for two nodes being shared, we have the uh, for a node being shared by two elements, we'll have common displacement term and common slope term. Right, this is the displacement, this is the slope, and likewise for shear force and moment term. So that's how we assemble this. I'll show you a bit of it later. First, we'll just go through it briefly. So one thing also unique about these problems is getting the boundary conditions. So now we have the for two second order equation we need two boundary conditions. Okay, and for fourth order equation we need four boundary conditions. So like we had earlier, we had one primary variable, one secondary variable. So one for each. Now we have two primary variables, two secondary variables. So one for each makes four boundary conditions. So uh, these are summarized here. I think you might have gone through this in class, and I need not elaborate this. This is, I think, very trivial. If there's any doubt, please let me know. So I think we are pretty much done here, and then we'll start the questions. So please let me know if there's any doubt, and then we'll start the questions. So I think if there's no doubt, we'll start with this problem. So as usual, I request your participation for these problems. Okay, so we have a 1D bar here. So temperature at this point is 50 degree, and left and other end is insulated. So can you tell me the boundary conditions Okay, I've written for first node. So can anyone tell me what should be the boundary condition for the other end of the bar? Please feel free to unmute yourself or just type in the chat box. Would anyone like to answer? Hello, you guys are there? Or am I audible? Can you please confirm? Please confirm. Are you guys following? Okay, I don't think anyone is responding. Anyways, I'll just go ahead. Okay. So we have one end at a fixed temperature, that's 50 degrees Celsius, and other end is kept insulated. Insulated means that there's no flux going in or out. That means the derivative of the variable is 0, or you can say the Q2 term is 0. Okay. So we have a heat generation, this small q of 5 watt per meter, and the thermal conductivity is 10 watt per meter per and the length of bar is 1 meter. So this is a general 1D heat conduction problem. Uh, so we'll keep it simple and we'll consider the one element, two noded one element. So heat conduction equation. Meanwhile, please confirm if you guys are following me, or even if I'm even audible to you guys. Q, I guess. Okay, no. Let's say. So this is what heat conduction equation looks like. We take the weak form. Can just do. Okay. So we consider W equals to psi I, T equals to Tj psi j. We get to 1. Sorry. Okay, so we can just, instead of solving it, we have the direct form for the matrix for this, and which is k by hg times 1 minus 1 minus 1 multiplied by the temperature vector equals to, we have q g by 2. Okay, we have 1, sorry. Okay, we have 1 here. Plus we have q1 and q2. Okay, so what do we know here? So here we know q2, that is 0, and we know t1 here, that is 50, and we know k here, k is 10. So and he is 1, so we're taking one element, and the length of bar is 1. We'll take 1, and all units are SI, so we need to worry about units. We have 10 by 1, so we'll get 10 minus 10 minus 10, 10 t t2. We have q as 5, I guess. Yeah, again h is 1, 5 by 2. We get 5 by 2, 5 by 2. Then we have q1 unknown and q2 is 0. So we just solve the equation. we can just take the second one first. So we have, okay, we'll write that normally. First equation is 500 minus 10 T2 equals to 5 by 2 plus Q1. Second equation is minus 500, and then we have plus 10 T2 equals again 5 by 2 on 0. So we have two equations, two unknowns. That's simple to solve. We get T2 as 500 minus 2.5 divided by 10 is 2.5. So we get, oh, sorry, 497.5 divided by 10. So T2 is 49.75 degrees Celsius. And we can also get Q1, but that's not what's asked in question. What is asked in question is the distribution of bar. So, I again would like your suggestion here. What should be the function for t here? Tx is a function of x. Would anyone like to volunteer to answer this? Do we have anyone who would like to answer? So we have a new joining just now, Mr. Prasan. Did you get what we are doing here? So can you hear me, right? So Mr. Prasan, are you there? Or am I audible? So I would like some input from your side. So we got the value at the nodes, but what should be the function for t, distribution function for a t in the entire domain? Are you guys with me? Can anyone confirm? Okay, if no one is answering, then I'll have to proceed. If you guys can get some input here, then it will be a, an interesting interaction. And otherwise, it becomes very monotonous. I keep on speaking. It's basically a doubt session. So in doubt session there should be interaction. You guys should ask something or some give some interference at least. Anyway, otherwise I'll go ahead. So uh, so when we decide the interpolation function, we or just forget it. We assume t here, right? T should be equals to tj size, summation of tj sizes. So a value node at each node should be multiplied by the corresponding shape function, and like that t2. So, so what is psi 1? Psi 1 is, I think, x b minus x 1 h, right? So it becomes, what is xp? 1. So it becomes 1 minus x. H is already 1. And psi 2 becomes x, x minus x. X minus x upon h. So we get x is 0. So we get just x, I guess. So we know the value t1, it is 50 times 1 minus x. And the value t2, 75, corresponding shape function. So this way we can get a function for the entire domain. And of course it's a linear function since we assumed it to be linear. So that's how you can get the value at any point. So if you want t equals to 0.5, just substitute t minus zero point 0.5 plus 49.75 times 0.5. You just get the average of the two. Since it's a the function would look something like this. So this is the bar. So model 1, 2. So this is a solution. This is 50. This is 49.75. And at half, you'll get the average of these two values. So this is somewhat a simple way of getting a solution. Not a simple way, but I mean I demonstrated the whole solution technique using a simple problem. Very simple. We just took one element, very simple, simple terms involved, no conjugate functions. So that's how basically you go ahead with the whole FEM formulation to solve any problem. So I hope this was clear here. If there's any doubt, you guys are welcome to and to stop me anytime. Okay, then second problem here is we have to find the boundary condition for the given beams here. So in first part we have at the left side we have a simple support. Okay, okay, fine, fine. So so am I audible, right? I'm not speaking to myself. Okay, uh, just wanted to confirm. Okay, so Mr. Paolo, if you're already here, then I would like to hear some direction from you. Would you mind helping me out in these problems? Yeah. Are we a solving exercise? And you're of course very much welcome to interfere me in between and ask doubts regarding this or regarding anything in the class that has been covered so far. Anything relevant, of course. So, anyways, we just did one question here. We solved a simple 1dy problem by considering one element for the entire domain, and we got some solution. And now we are doing this problem where we have to uh, identify boundary condition for a given for the given beams. So in first part, we are giving a simple support at the left end and a fixed support at the right end. So, so at the left end, what should be the boundary conditions? So we have four things, right? We have W, we have theta, we have shear force, and bending. So what can we say about each of these? Do we know any of these things? Would Would anyone like to answer this? Okay. How does it affect the matrices? I think uh, if you have done the past classes, it's just the same as before. After applying boundary conditions, you get the value for the unknown. So if I take this, the last question that we did here, so we have this kind of formulation here, right? This thing. So we had four unknowns here: T1, T2, Q1, Q2, and if, as you can see, there are only two equations but four unknowns. So the other two unknowns are taken from the boundary condition. That's it. So we in the given problem we knew the temperature at one node and we knew the flux condition at the other node. It's insulated. So we just straight away substituted these values here and we got a simplified equation here. Sorry. Yeah. So we got this kind of equation here. So we are just left with two variables. We can simply solve these equations. That's how we apply boundary conditions. In terms of shift, if we're talking about directly in terms of matrices and vectors, mm, in so if we have some, so are you aware about applying boundary conditions in case of simple 1D uh, bar problem or heat conduction problem? Are you aware about that? Okay, maybe we distinguish between essential and natural condition, primary, secondary variables as first thing. Uh, I didn't get it very well. We distinguish between essential and natural condition, primary and secondary variables as first thing. Mm, kind of. Yeah, sure. So that's a separate thing. Apart from getting the equations in terms of these matrices and vectors, uh, knowing the boundary condition is a parallel separate thing. So both the things come up together to suffice to uh, get equal known conditions as the number of variables. That's the thing. So just like this, we had two equations here in this case, but four variables. So we need to know the boundary conditions in order to get this. So it's not like the first thing to do, but it's there. It's important to know. I hope that's fine. So should we go ahead? Is there any more doubt, or should I continue? Okay. Okay, then we will proceed. So at left end we have a simple pin support, and we know that this bar cannot move up and down at this point. This is not allowed here. So this is definitely going to be zero. But it can deflect here. So like this. So we can definitely have some slope here. So we don't know this slope. And of course, if there's a pin support, we'll surely get a reaction. So we don't this bound to be shear force, and we don't know it. But it can't have a pin cannot generate a moment reaction. So that's surely going to be zero. These are the two things that we know here. So we just remove this, and drag it together. So we know the bending moment, and it is going to be zero. On the right end, it can't move up and down. So definitely displacement zero, and even it can't even uh, tilt like this or like this. It's always going to bend like this or this. So we see the slope is always going to be zero. So this should be the four boundary conditions for this problem, this kind of thing. Okay, and for the next problem on left hand we have theta. Okay, anyone would like to guess? What all do we know on the left hand here? The second part, B part. Theta unknown and shear force known. Okay, theta is unknown, right? Shear force is known, right? What should be the value of shear force? Can we tell the value of shear force from here? Force applied, right? Yeah, can you give me the sign and magnitude of the force applied? Uh, Particularly, I want to know the sign. Of course, we don't know W also by equilibrium condition. No, we don't know, need to go so far. Whatever the thing is applied here, that is the boundary condition. We have the magnitude as 5, but what should be direction? Excuse me. So we're talking about the left hand, just left hand. 5 is the value, the point. Yeah, it is a value, but this would give, we would know the value of shear force at this end. If it's there's a point load applied at any free end, not any fixed offend end, then we surely know the value of shear force at that end, and that is the one that is applied there. So here it's a 5, but since it's applied downward, yeah, bending moment is zero, of course. There's no moment applied here, so bending moment will be zero. And force would be minus 5 since it's downwards and R conventional. Say that. And what do we have on the right side? Okay, right hand side is again the same. So without any ado, we just write this. Okay. Okay, I think this is fine. Yeah, check right side bending moment and shear force both are unknown. You just know the displacement and the slope. That is surely going to be zero for a fixed. Shear force is on the left side. It's not 5. It's -5 actually. Okay, you mean on the right side? Yeah, yeah. We can know that using equilibrium condition, but we won't do that here because in FEM we just follow the equation and get the answer by that the FEM procedure, not by applying the equilibrium equation. Okay, so how do we write the Q vector? Q vector has four terms. So first one is the shear force at point 1, then one the bending moment is point 1, third one is shear force point 2, fourth one is bending moment is point 2. So for first part, do we know the shear force and bending moment with two ends? Okay, at the left hand. So in order to write the Q vector, we just need to know the shear force and bending moment. So we don't know the shear force. So we can keep it as an unknown Q1. Excuse me. And the bending moment is going to 0. So we can just write 0. And on the right side, yes, right. These are only applied. They can be so here at the left end, since shear force is not known, right? We'll just write it as Q1. But we know the U value here. Sorry, the vertical displacement here, W. So in the corresponding equation, when we'll substitute the value of W and everything, from there we can get this value of reaction here, Q1. So uh, initially we just go with whatever the things we know, and the unknown things are the reactions only. We keep them as unknown. We keep them as a variable in the equation and solve them to get these reactions. So on the right side we have shear force is 0, nothing is applied. And what is the value of bending moment on right side? Plus 6. Uh, the direction is anti-clockwise. So I think what we uh, took the convention was clockwise to be positive. Is it? Yeah, it's anti-clockwise. So I think we'll take -6 here. So what the Q we'll get here is for part A, we'll get as Q1 0 and 0 minus 6. So you'll see the corresponding u vector, you would have this known. This should be 0. And the other 3 would be unknown. So 2, 3, 4. So you see, if we know one thing, we wouldn't know the other thing. So we'll have to solve the equation to get the other thing. So this would be the u vector for. So you see, that's how we apply the boundary condition. We substitute the corresponding value of q and u in the vectors. And for here, the second problem, there's no shear force on that side. There's a bending moment. So it's 2. What should be the sign for this? Minus 2. No, no, it's see, the direction is uh, clockwise. Yeah, it's plus 2. Nice. And the right side we have shear force as 10. So what should be the direction of shear force here on the right side? Minus 10. No, we're taking upward as positive. Yeah, we'll take it as plus 10. And the bending moment is 0. Nothing is given. So we know everything here in Q. So for part B, we have QS 0, 2 and 10, 0. So third part, what would be the shear force here? Bending moment, nothing is there, it's 0. What would be the shear force? KW, right? But with a negative sign, because the force upward would come only when the deflection is downwards, minus W. So we have KS 10, so we'll have 10 times W, or we can call this as U1. And on the right side, we know no shear force. Q3, we don't know bending moment. Q4. So what should be the Q for this part? 10, sorry, minus 10. 0, Q3 and Q4 unknowns. And the corresponding U would be, we have US, U1 unknown, but same unknown. So we'll only have one variable here. And here this is unknown, and these two would be known. So we are again left with four unknowns and four equations after applying the boundary conditions. Okay, I hope this much is clear. Yeah, right, exactly. That's the whole point of boundary conditions actually. You need to fix certain things at the boundaries to get some uh, system of what do we call this system of equations, uh, which have definite solution, right? Otherwise, it would be indefinite number of solutions when we have more variables in the equations. We have yeah, infinitely many solutions. I don't remember What's the term for that system of equations? Okay. So I hope this much was clear. Uh, do you have any doubts here, or should we stop now, or do you want some more problems to be solved? Please let me know. I would have wanted the Timoshenko beam is different in its assumptions. So that type of beam is that type of the assumptions involved a relatively thicker beam compared to Euler-Bernoulli beams. So we have considerable, I think, shear deformation or something across the cross section. So here everything is, I think, same in no. Yeah, I think there's some shear deformation in the across the crossing. I'm not sure. I haven't gone through Timoshenko beam, but the one thing I know that is for relatively thicker beams. So you'll get another term in your governing equation. So for your Euler-Bernoulli beam, your governing equation look something like this: E dx square. In Timoshenko beam, you get some one more term here equals to fx that accounts for the deformation across the thickness. Okay, this was clear. Yeah. Is there any other doubt? Please feel free to ask. I wanted to solve some beam problem also, just like I solved the 1D heat equation problem, but that would take a lot of time. The equations are not very like the 4 by 4 matrix, the shape functions are very complicated. It would take a lot of time to solve these things. If you want, I can do it maybe next class. Okay, so please let me know if there's any more doubt, or we can wrap up the session. Apart from sign convention, uh, uh, there's nothing too complicated about sign convention. There's just one thing you need to follow. Just stick with it, whatever it is. So here what we have done is taken upward as positive and clockwise as positive. In case of deflection and shear force, we have upward and downward. And in case of slope and bending moment, we have clockwise and anti-clockwise. So we have taken upward as positive and clockwise as positive. That's it. Just stick to it and you'll be good to go. Both right and left. Yes, I think so. I think so. There, to my knowledge, there isn't any distinction for that. In case of applied force, I mean, in case of these applied moments and forces, I don't think there's any distinction. I remember in strength of materials when we used to solve beam problems using equilibrium equation, all those things. When we used to draw bending moment and shear force diagram, there was a distinction, but here their thing different was we used to take sections of the beam to consider all those things. So when we take sections off, we get reaction forces. So those are opposite in direction, and there's something like that. So there's something needs to change. I'm not sure about that. I'll dig it, and maybe next time I'll confirm your answer. But to my knowledge, here for these problems, we don't need to worry about if it's from left side or right side. Okay, uh, it's fine. Please let me know if there's any more doubts. Okay, then if there are no doubts, then we can wrap up the session. And I thank you all for your participation, and hope to see you soon for the coming sessions. I think you have your exam by the end of this month, right? 25th September. I hope you are preparing well for it. And if there's any doubt in between, you can contact me anytime. I think there's a Google discussion forum for this. I tried to answer the doubts there. You might have seen my email there, so you can even ping me if I'm not responding. Okay, then we can wrap up now. Thank you. Thank you, everyone.